Habitable exoplanets, a meditative journey through Earth-like worlds. Somewhere beyond our solar system, orbiting distant stars scattered across the Milky Way galaxy, worlds exist that might harbor the gentle conditions necessary for life. These exoplanets, planets beyond our sun's influence, represent one of humanity's most profound questions made tangible. In the darkness of space, separated by distances so vast they challenge comprehension, these distant worlds continue their ancient dance around foreign suns, some perhaps covered in oceans, others wrapped in atmospheres that could sustain the delicate chemistry of living things. The search for habitable exoplanets connects us to something fundamental about our place in the universe. Each discovery brings with it the possibility that Earth is not alone in hosting the intricate processes that create and sustain life. As telescopes peer deeper into space and instruments become more sensitive, astronomers continue to catalog worlds that exist in that narrow band around their stars, where liquid water can persist on a planetary surface, a region scientists call the habitable zone, or sometimes the Goldilocks zone, where conditions are neither too hot nor too cold, but just right. Tonight, as the Earth turns slowly beneath a canopy of stars, each pinpoint of light in the sky potentially hosts its own family of worlds. Some of these planets may be rocky like Earth, with solid surfaces carved by ancient impacts and shaped by geological forces. Others might be water worlds, covered entirely by deep oceans that have never known the touch of dry land. In the gentle darkness of space, these distant Earths continue their journeys, carrying within their atmospheres and across their surfaces the ongoing experiments of planetary evolution. The habitable zone, where life finds its balance. Around every star in the galaxy, there exists an invisible sphere of possibility, a region where the temperature conditions allow liquid water to exist on the surface of an orbiting planet. This habitable zone stretches outward from each star like a cosmic comfort zone, its boundaries determined by the star's brightness and heat output. For our Sun, this zone begins somewhere around the orbit of Venus and extends past Mars, with Earth sitting comfortably in the middle, bathed in just the right amount of stellar energy to maintain oceans in their liquid state. The concept seems deceptively simple, yet the habitable zone represents a delicate balance of cosmic forces that have been refined over billions of years. Too close to the star, and a planet's water boils away into space, leaving behind a scorched, airless world like Venus, where surface temperatures reach nearly 900 degrees Fahrenheit, hot enough to melt lead. Too far away, and water freezes into ice, creating frozen landscapes where any potential for life as we know it becomes locked away in solid form, waiting for some future warming to release it back into the realm of possibility. The width of a star's habitable zone depends entirely on that star's characteristics. Massive, bright blue stars burn with such intensity that their habitable zones stretch far outward. But these stellar giants live fast and die young, burning through their nuclear fuel in just a few million years. Barely enough time for complex life to develop on any orbiting worlds. Red dwarf stars, on the other hand, burn so dimly that their habitable zones huddle close to the star's surface, where tidal forces might lock planets in permanent day and night hemispheres, creating worlds of eternal noon and eternal midnight. Between these extremes lie the K-type stars, sometimes called orange dwarfs, which burn with a gentle, steady light that lasts for tens of billions of years. These stars, slightly smaller and cooler than our Sun, create habitable zones that remain stable for geological ages, providing the long-term consistency that complex life might require. Their orange glow bathes any orbiting worlds in light that appears softer and warmer than our sun's, creating what some astronomers playfully call Goldilocks stars, stellar environments that seem perfectly suited for nurturing life over cosmic timescales. The habitable zone also shifts and changes as stars age. Young stars burn brighter and hotter, gradually settling into a steadier output as they mature. This means that a planet might start its existence outside the habitable zone, slowly warming as its star stabilizes, or begin in comfortable temperatures only to see conditions change as stellar evolution progresses. The history of any potentially habitable world becomes a story of adaptation and survival, as planetary conditions respond to the changing output of their host star over millions and billions of years. Now, close your eyes and picture how all of this might look. Imagine floating in space above one of these distant worlds, watching as it orbits its orange-tinted star. The planet appears as a blue marble against the darkness, its surface painted with the familiar patterns of continents and oceans. But the light illuminating this world carries a different quality than Earth's sunlight. Warmer, more amber, casting everything in hues of gold and orange. The planet turns slowly beneath you, revealing weather patterns that swirl across unknown continents, and ice caps that glisten at the poles under the alien star's steady glow. Host stars, the cosmic hearths of distant worlds. The stars that host potentially habitable planets span a range of types, each creating unique conditions for any worlds that orbit within their gravitational embrace. Our Sun belongs to the category known as G-type stars, medium-sized yellow-white stars that burn hydrogen in their cores at a steady rate, maintaining consistent energy output for around 10 billion years. This stellar longevity provides the stable conditions necessary for the slow development of complex life, giving biological processes time to establish themselves and evolve into increasingly sophisticated forms. K-type stars, those slightly smaller orange dwarfs, have emerged as particularly promising targets in the search for habitable worlds. These stars burn their nuclear fuel more slowly than our Sun, extending their stable lifetimes to 20 billion years or more, twice as long as our own star's expected lifespan. This extended period of steady energy output creates what astronomers call an extended habitable zone lifetime, providing ample time for life to not only emerge, but to develop into complex, possibly intelligent forms. The light from K-type stars bathes their planets in wavelengths that penetrate atmospheres efficiently, potentially supporting photosynthesis-like processes that could form the foundation of alien ecosystems. The reduced ultraviolet radiation from these cooler stars also means less damage to delicate organic molecules, creating environments that might be more conducive to the preservation and evolution of life. Around these orange suns, worlds could exist where the sky appears perpetually bathed in the warm light of sunset, where the gentler stellar output allows atmospheres to retain their complexity without being stripped away by harsh radiation. Red dwarf stars, the most common type in the galaxy, present both opportunities and challenges for habitability. These small, cool stars burn so slowly that they can maintain steady energy output for trillions of years, lifetimes so long they dwarf the current age of the universe. However, planets in the habitable zones of red dwarfs orbit so close to their stars that they become tidally locked, with one hemisphere permanently facing the star in eternal day, while the other remains in perpetual night. This creates worlds of extreme temperature contrasts, where the day side might be scorchingly hot, while the night side remains frozen solid. Yet even tidally locked worlds might support life under certain conditions. Thick atmospheres could redistribute heat from the day side to the night side, creating regions along the terminator line, the boundary between day and night, where temperatures might remain moderate enough for liquid water to exist. These twilight zones could harbor ecosystems adapted to the permanent sunset conditions, where life finds a way to thrive in the gentle transition between the extremes of eternal day and endless night. The most massive stars, the blue giants that burn with fierce intensity, create habitable zones so far from their surfaces that any orbiting planets would exist in vast, cold orbits. But these stellar titans burn through their nuclear fuel in just a few million years before exploding as supernovas, scattering heavy elements across space, but providing insufficient time for complex life to develop on any worlds that might orbit within their habitable zones. These stars serve instead as the universe's element factories, forging the carbon, oxygen, nitrogen, and other materials that eventually find their way into the rocky planets and atmospheres of longer-lived stellar systems. White dwarf stars, the remnants left behind when sun-like stars exhaust their nuclear fuel, can also host habitable zones, though these regions exist much closer to the stellar remnant's surface. These compact objects, no larger than Earth but containing the mass of our Sun, glow with residual heat that slowly fades over billions of years. Planets orbiting in the habitable zones of white dwarfs would experience conditions quite unlike those around main sequence stars. Shorter years, intense but slowly dimming light, and the knowledge that their star's energy source is finite, gradually cooling toward an inevitable cosmic winter. Atmospheric signatures, reading the breath of distant worlds. The atmosphere of a potentially habitable planet serves as both its protective shield and its cosmic fingerprint, a gaseous envelope that not only determines surface conditions, but also broadcasts the planet's characteristics across interstellar space. When starlight passes through a planet's atmosphere during transit, certain wavelengths of light get absorbed by atmospheric gases, creating a unique spectral signature that astronomers can detect and analyze from thousands of light years away. These atmospheric fingerprints tell the story of a world's composition, climate, and potentially its biological activity. Water vapor represents perhaps the most crucial atmospheric component for life as we understand it. The detection of water vapor in an exoplanet's atmosphere suggests the presence of liquid water somewhere on or within the planet, either as surface oceans, subsurface reservoirs, or atmospheric humidity from active water cycles. Water vapor absorption lines appear distinctly in infrared light, creating spectral features that modern telescopes can identify even around distant worlds. The amount of water vapor detected can indicate whether a planet maintains active weather systems, with clouds forming and dissipating as water evaporates from surface reservoirs and condenses back into precipitation. Oxygen presents a more complex atmospheric signature, particularly in its molecular form. On Earth, nearly all atmospheric oxygen comes from photosynthesis, the biological process by which plants and certain microorganisms convert carbon dioxide and water into organic compounds, releasing oxygen as a byproduct. Free oxygen in an atmosphere represents a highly reactive gas that would quickly combine with other chemicals if not continuously replenished by biological processes. The detection of significant amounts of oxygen in an exoplanet's atmosphere, especially when combined with water vapor, could represent one of the strongest indicators of active biology on a distant world. Methane adds another layer of complexity to atmospheric analysis. This simple hydrocarbon can be produced both by geological processes and by living organisms. On Earth, much of the atmospheric methane comes from biological sources: bacteria in wetlands, digestive processes in animals, and human activities. But methane can also be released by volcanic activity, serpentinization reactions in crustal rocks, or impacts from methane-rich comets and asteroids. The key lies in the ratios and combinations of atmospheric gases. Methane and oxygen together create a particularly interesting signature, as these gases react with each other in the atmosphere. Their simultaneous presence suggests active replenishment from surface sources, possibly biological ones. Carbon dioxide serves as both a greenhouse gas that helps regulate planetary temperature and a raw material for photosynthesis. The amount of carbon dioxide in an atmosphere can indicate a planet's position in the habitable zone and the strength of its greenhouse effect. Too little carbon dioxide, and a planet might be too cold to maintain liquid water. Too much, and runaway greenhouse effects could create surface conditions like those on Venus, where dense carbon dioxide atmosphere creates crushing pressure and temperatures hot enough to melt metal. The balance of carbon dioxide with other atmospheric components helps astronomers understand whether a planet maintains the delicate equilibrium necessary for surface habitability. Ozone, formed when oxygen molecules are broken apart by ultraviolet light and reassemble into 3 atom molecules, creates another potential biosignature. Ozone absorption features appear prominently in ultraviolet and visible light spectra, and substantial ozone concentrations typically require abundant atmospheric oxygen as a precursor. An ozone layer also serves as a protective shield, blocking harmful ultraviolet radiation that could damage surface life. The detection of ozone in an exoplanet's atmosphere might indicate not only the presence of biological oxygen production, but also surface conditions protected enough for complex life to flourish. Advanced spectroscopic techniques now allow astronomers to search for even more subtle atmospheric components that might indicate biological activity. Dimethyl sulfide, produced by marine algae on Earth, creates distinctive absorption features that could theoretically be detected in the atmospheres of distant water worlds. Phosphine, recently detected in the atmosphere of Venus, represents another gas that on Earth is primarily produced by biological processes, though its presence around other worlds could have alternative explanations. Now, close your eyes and picture how all of this might look. Imagine standing on the surface of a world orbiting a distant K-type star, breathing air that carries the sweet scent of oxygen and water vapor. Above you, clouds drift across an alien sky tinted amber by the orange star's light. The atmospheric composition around you represents billions of years of planetary evolution, gases cycling between surface and sky. Each breath you take containing molecules that have traveled through countless chemical processes, some perhaps touched by the metabolic activities of alien life forms that have shaped this world's atmospheric signature across geological ages. If this peaceful view of the cosmos brings you calm, consider returning here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. Water worlds and magnetic shields. The essential ingredients. Water exists as the universal solvent that makes complex chemistry possible, and magnetic fields serve as invisible shields that protect planetary atmospheres from the erosive effects of stellar radiation. Together, these two factors create the fundamental conditions that allow worlds to maintain the stable, long-term environments where life might take hold and flourish over cosmic timescales. The presence of liquid water on a planetary surface depends on a delicate balance of factors that extend far beyond simply orbiting within the habitable zone. Atmospheric pressure plays a crucial role. Without sufficient atmospheric density, water would boil away even at moderate temperatures, as happens on Mars today. The thin Martian atmosphere creates surface pressures so low that liquid water cannot exist stably, despite temperatures that occasionally reach above freezing. Conversely, extremely dense atmospheres can trap heat so effectively that surface temperatures remain far too hot for liquid water, as demonstrated by the crushing, scorching environment beneath Venus's thick carbon dioxide atmosphere. Planetary size influences a world's ability to retain both its atmosphere and its water over geological timescales. Larger planets possess stronger gravitational fields that can hold on to atmospheric gases more effectively, preventing them from slowly bleeding away into space. But planets that are too massive might accumulate thick hydrogen atmospheres during their formation, creating mini-Neptune worlds with surface pressures that would preclude the existence of exposed liquid water. The ideal size appears to fall within a range similar to Earth, large enough to maintain atmosphere and geological activity, but not so large as to retain primordial gases that would create crushing surface conditions. The role of plate tectonics in maintaining surface water involves a complex cycle that regulates planetary temperature over millions of years. On Earth, the movement of crustal plates allows carbon dioxide to be absorbed by weathering rocks and then released back into the atmosphere through volcanic activity. This geological thermostat helps maintain temperatures within a range suitable for liquid water, even as the sun's brightness has increased by about 30% since life first appeared on our planet. Worlds without active plate tectonics might lose this regulatory mechanism, potentially leading to either runaway greenhouse effects or global freezing as atmospheric composition gradually changes. Magnetic fields generated by a planet's core create protective bubbles around worlds, deflecting charged particles from stellar wind that would otherwise strip away atmospheric gases. Earth's magnetic field, generated by convection currents in our planet's liquid iron core, extends tens of thousands of miles into space, creating the magnetosphere that shields our atmosphere from the constant stream of charged particles flowing outward from the sun. Without this protection, atmospheric gases would gradually be blown away into space, as appears to have happened to Mars after its magnetic field weakened billions of years ago. The strength and configuration of a planet's magnetic field depends on several factors, including the size of the metallic core, the planet's rotation rate, and the convection patterns within the molten interior. Rapidly rotating planets with large, active cores generate the strongest magnetic fields, creating the most effective protection for surface environments. Some exoplanets might possess magnetic fields much stronger than Earth's, potentially creating magnetospheres that extend even further into space and provide enhanced protection for atmospheric retention and surface habitability. Tidal heating represents another mechanism by which some worlds maintain liquid water, even outside the traditional habitable zone. Moons orbiting large planets experience gravitational forces that flex their interiors, generating heat through friction. Europa, orbiting Jupiter, maintains a subsurface ocean beneath its icy crust through exactly this process, despite receiving only a fraction of the sunlight that Earth does. Similar tidal heating could allow moons around gas giant exoplanets to harbor liquid water environments, greatly expanding the number of potentially habitable worlds beyond those orbiting within stellar habitable zones. The composition of a world's water inventory also affects its habitability potential. Pure water oceans might lack the dissolved minerals necessary for complex chemistry, while overly saline conditions could create environments too extreme for most biological processes. The ideal balance includes dissolved carbonates, sulfates, and other minerals that facilitate the chemical reactions underlying life's processes. The source of a planet's water, whether delivered by comets during early bombardment periods, outgassed from volcanic activity, or retained from the original accretion process, influences the final composition of surface oceans and their suitability for supporting life. Recent discoveries by the James Webb Space Telescope. The James Webb Space Telescope has transformed our understanding of exoplanet atmospheres by providing unprecedented detail in the analysis of distant worlds. This infrared observatory, positioned at a gravitationally stable point nearly 1 million miles from Earth, uses its massive mirror and sensitive instruments to capture light that has traveled across vast interstellar distances, carrying within its spectral signatures the atmospheric secrets of planets orbiting other stars. One of Webb's most significant contributions to exoplanet science involves the detailed atmospheric analysis of WASP-96b, a gas giant located about 1,100 light-years from Earth. While this particular world is far too hot and massive to support life as we know it, Webb's observations revealed the presence of water vapor, clouds, and atmospheric haze with a level of detail previously impossible to achieve. The telescope detected specific wavelengths of light absorbed by water molecules in the planet's atmosphere, creating a spectral fingerprint that demonstrates the precision with which modern instruments can analyze the atmospheric composition of distant worlds. The telescope's observations of the TRAPPIST-1 system have provided crucial insights into the atmospheric retention capabilities of small, rocky planets. This system, located about 40 light-years from Earth, contains 7 Earth-sized worlds orbiting an ultra-cool red dwarf star. Webb's initial observations focused on TRAPPIST-1b, the innermost planet, revealing that this world likely lacks a substantial atmosphere, probably due to the intense stellar radiation it receives from its close orbit around the red dwarf. These findings help scientists understand how stellar activity affects atmospheric retention on small planets, providing important constraints for habitability assessments of similar worlds. K2-18b represents one of Webb's most intriguing discoveries in the realm of potentially habitable worlds. This sub-Neptune exoplanet, about 2.5 times larger than Earth and located about 120 light-years away, orbits within the habitable zone of its cool dwarf star. Webb detected both water vapor and carbon dioxide in the planet's atmosphere, along with possible signs of dimethyl sulfide, a molecule that on Earth is only produced by biological processes. While the planet's large size suggests it might be more like a mini Neptune than a terrestrial world, the atmospheric detections demonstrate Webb's capability to analyze the chemical compositions of potentially habitable atmospheres. The telescope's observations have also revealed the complex atmospheric dynamics of hot Jupiter exoplanets, providing insights into atmospheric circulation patterns that help scientists understand how atmospheres behave under extreme conditions. WASP-43b, a planet where temperatures exceed 2,000 degrees Fahrenheit, shows dramatic temperature differences between its day and night sides, with Webb mapping these variations across the planet's surface. Such observations help refine atmospheric models that scientists use to predict conditions on more temperate worlds. Webb's infrared capabilities have proven particularly valuable for detecting atmospheric water vapor, which absorbs specific wavelengths of infrared light. The telescope can measure not just the presence of water vapor, but also its abundance and distribution within an atmosphere. These measurements provide insights into atmospheric circulation patterns, cloud formation processes, and the overall water cycle dynamics that might exist on distant worlds. The telescope's observations of planetary formation regions have also enhanced our understanding of how potentially habitable worlds develop. By studying protoplanetary disks around young stars, Webb can observe the raw materials from which terrestrial planets form, including the water-rich ices and organic compounds that eventually become incorporated into rocky worlds. These observations reveal that the building blocks of habitability are common throughout the galaxy. present in the formation zones of stellar systems across a wide range of stellar types and environments. Webb's precise photometry capabilities allow for the detection of subtle atmospheric features that previous telescopes could not resolve. The instrument can distinguish between different molecular species in exoplanet atmospheres, providing detailed chemical inventories that help scientists assess the potential habitability of distant worlds. As Webb continues its observations over the coming years, it will build an increasingly comprehensive catalog of exoplanet atmospheric compositions, greatly advancing our understanding of how common, potentially habitable conditions might be throughout the galaxy. Now, close your eyes and picture how all of this might look. Imagine the James Webb Space Telescope floating silently in the darkness of space, its golden mirror reflecting starlight as it peers across impossible distances toward other worlds. Light that left distant planets years or decades ago finally reaches the telescope's detectors, carrying within its spectral patterns the chemical signatures of alien atmospheres. Each photon tells a story of conditions on worlds so far away that their existence was unknown just a few decades ago. Yet now their atmospheric compositions can be measured with extraordinary precision. The Habitable Worlds Observatory, humanity's next great eye. The Habitable Worlds Observatory represents humanity's next major leap forward in the search for Earth-like worlds and potential signs of life beyond our solar system. This ambitious space-based telescope mission, currently in the early planning stages, will be specifically designed to directly image potentially habitable exoplanets and analyze their atmospheric compositions with unprecedented precision and sensitivity. Unlike current instruments that primarily detect exoplanets through indirect methods, such as transit photometry or radial velocity measurements, the Habitable Worlds Observatory will employ advanced coronagraph technology to block out the overwhelming brightness of host stars, allowing for direct observation of much fainter orbiting planets. This capability represents a monumental technical achievement, as the brightness difference between a star and an orbiting Earth-like planet can be as extreme as 10 billion to 1, equivalent to trying to spot a firefly hovering next to a searchlight from thousands of miles away. The observatory's primary mirror will likely measure between 6 and 8 meters in diameter, providing the light-gathering power and resolution necessary to separate the faint light of distant planets from the glare of their host stars. Advanced adaptive optic systems will continuously adjust the mirror's shape to compensate for tiny vibrations and thermal fluctuations that could blur the delicate images of distant worlds. The entire instrument will operate at extremely cold temperatures, reducing thermal noise that could interfere with the detection of faint planetary signals. Sophisticated spectrographic instruments aboard the observatory will analyze the light reflected or emitted by directly imaged exoplanets, revealing detailed information about their atmospheric compositions. These instruments will be sensitive enough to detect biosignature gases such as oxygen, ozone, water vapor, and methane in the atmospheres of Earth-sized planets orbiting sun-like stars. The combination of multiple atmospheric signatures could provide compelling evidence for biological activity on distant worlds, representing humanity's first definitive detection of life beyond Earth. The observatory's coronagraph technology will employ several complementary approaches to suppress starlight while preserving planetary signals. Vortex coronagraphs use specially designed masks that create destructive interference patterns, effectively canceling out light from the central star while allowing light from orbiting planets to pass through. Starshade technology involves a separate spacecraft flying in precise formation with the telescope, positioning a flower-shaped occulter between the telescope and target stars to physically block starlight before it reaches the primary mirror. The mission will target several hundred nearby stars, focusing on those most likely to host potentially habitable worlds. G-type stars, like our Sun and K-type orange dwarfs, will receive priority attention, as these stellar types provide stable, long-lived energy sources that could support the development of complex life over geological timescales. The observatory will search for planets within the habitable zones of these stars, looking for worlds that receive similar amounts of stellar energy as Earth. Advanced data analysis techniques will help scientists interpret the wealth of information gathered by the observatory. Machine learning algorithms will assist in identifying atmospheric signatures and distinguishing between biological and non-biological sources of potentially interesting gases. The observatory's observations will be combined with theoretical models of planetary atmospheres and climate systems to provide comprehensive assessments of habitability conditions on discovered worlds. The Habitable Worlds Observatory will also conduct detailed studies of planetary system architectures, revealing how Earth-like worlds fit within the broader context of their stellar systems. The presence or absence of gas giant planets in outer orbits, the distribution of asteroidal debris, and the overall dynamical stability of planetary systems all influence the long-term habitability prospects of terrestrial worlds. Understanding these system-wide factors will help scientists assess which discovered planets are most likely to maintain stable, habitable conditions over billions of years. The technological advances developed for the Habitable Worlds Observatory will push the boundaries of precision engineering, optical design, and space-based operations. The coronagraph systems require optical stability measured in picometers, distances smaller than the diameter of individual atoms. The spacecraft's pointing accuracy must be maintained to within millierk seconds, equivalent to the angular size of a quarter viewed from a distance of about 1,000 miles. These extreme precision requirements are driving innovations in materials, science, control systems, and space-based instrumentation. Detection methods: how we find worlds in the dark. The discovery of exoplanets orbiting distant stars requires ingenious techniques that push the limits of observational astronomy, as these worlds remain invisible to direct observation from Earth's distance. Over the past 3 decades, astronomers have developed multiple methods for detecting the subtle gravitational, photometric, and spectroscopic signatures that reveal the presence of planets around other stars. Each technique providing different insights into the characteristics and orbital properties of these distant worlds. The transit method has proven to be the most productive technique for exoplanet discovery, responsible for finding thousands of confirmed planets since the launch of dedicated space-based missions. When a planet passes directly between its host star and Earth, it blocks a tiny fraction of the star's light, creating a periodic dimming that sensitive photometers can detect. The amount of light blocked reveals the planet's size relative to its star, while the duration and shape of the transit provide information about the planet's orbital period and distance from its host star. Space telescopes like Kepler and TESS have used this method to survey hundreds of thousands of stars simultaneously, creating vast catalogs of transiting exoplanets. The precision required for transit detection is extraordinary. Earth-sized planets orbiting sun-like stars block only about 80 parts per million of their star's light, equivalent to the dimming caused by a single grain of sand passing in front of a powerful spotlight. Modern space telescopes achieve photometric precision measured in parts per million, allowing them to detect these incredibly subtle signals against the natural brightness variations of stars themselves. Ground-based telescopes can detect larger transiting planets, but atmospheric turbulence typically limits their precision to detecting Neptune-sized or larger worlds. Radial velocity measurements detect the gravitational influence of orbiting planets on their host stars by observing tiny Doppler shifts in stellar spectral lines as stars wobble back and forth in response to planetary gravitational tugs. This technique, sometimes called the wobble method, can determine both the minimum mass of orbiting planets and their orbital periods. Jupiter-mass planets orbiting close to Sun-like stars create stellar velocity changes of several hundred meters per second, easily detectable with modern spectrographs. Earth-mass planets in habitable zone orbits produce much smaller signals, requiring velocity precision of about 1 meter per second, roughly walking speed. The combination of transit and radial velocity measurements provides comprehensive characterization of exoplanet properties. Transit observations reveal planetary radius and orbital characteristics, while radial velocity measurements determine planetary mass. Together, these measurements allow astronomers to calculate planetary density, providing crucial insights into whether worlds are rocky like Earth and Mars, icy like Europa and Enceladus, or gaseous like Jupiter and Saturn. This density information helps scientists assess which discovered planets might possess solid surfaces suitable for habitability. Direct imaging represents the most challenging but potentially most informative exoplanet detection method, requiring advanced coronagraph technology to block the overwhelming brightness of host stars, while revealing the much fainter light from orbiting planets. Only a few dozen exoplanets have been directly imaged, typically large, young planets orbiting far from their stars, where the brightness contrast is more manageable. Direct imaging allows for spectroscopic analysis of planetary atmospheres and can potentially detect biosignature gases that might indicate biological activity. Gravitational microlensing exploits the gravitational focusing effect predicted by Einstein's theory of general relativity to detect planets around distant stars. When a foreground star passes almost directly between Earth and a more distant background star, the gravitational field of the foreground system acts as a natural telescope, magnifying and brightening the background star's light. Planets orbiting the foreground star create additional brightening events that reveal their presence and approximate mass. This technique is particularly sensitive to planets orbiting at distances similar to Earth's orbit around the Sun. Astrometry measures the tiny positional shifts of stars caused by gravitational interactions with orbiting planets. As planets orbit their stars, the gravitational interaction causes both objects to orbit around their common center of mass, creating measurable stellar motion across the sky. The European Space Agency's Gaia mission has achieved the precision necessary to detect these minute stellar motions, potentially discovering thousands of new exoplanets through astrometric measurements over its multi-year mission duration. Pulsar timing represents a specialized detection method that uses the incredibly precise radio pulses from neutron stars as cosmic clocks to detect orbiting planets. Planets around pulsars cause tiny timing variations in the arrival of radio pulses at Earth, revealing the presence and characteristics of these exotic worlds. While pulsar planets exist in environments far too hostile for life, their discovery demonstrated that planet formation can occur even around the remnants of stellar explosions. The combination of multiple detection methods provides increasingly complete pictures of individual planetary systems. Follow-up observations using different techniques can confirm initial discoveries, refine planetary parameters, and reveal additional planets that might have been missed by single-method surveys. As detection methods become more sensitive and precise, astronomers continue to push toward the ultimate goal of detecting and characterizing truly Earth-like planets orbiting within the habitable zones of nearby Sun-like stars. Now, close your eyes and picture how all of this might look. Imagine Earth's most sensitive telescopes turned toward the night sky, their enormous mirrors and precise instruments gathering ancient starlight that has traveled across the galaxy. In control rooms bathed in the soft glow of computer monitors, astronomers analyze streams of data, searching for the tiny periodic dips in brightness that reveal distant worlds crossing in front of their stars. Each detection represents a moment of cosmic discovery, the realization that another world exists in the vast darkness, orbiting its star in patterns as regular and predictable as the motions of planets in our own solar system. If this peaceful view of the cosmos brings you calm, consider returning here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. The quest for Earth's twin among billions. Within the vast expanse of the Milky Way galaxy, containing an estimated 100 billion stars, the statistical likelihood suggests that millions or perhaps billions of worlds exist with conditions similar to Earth. Yet finding a true Earth twin, a rocky planet of similar size, orbiting within the habitable zone of a sun-like star, with an atmosphere capable of supporting liquid water, represents one of the most challenging quests in modern astronomy. The search for Earth's twin requires not just detecting distant planets, but characterizing their properties with sufficient precision to identify worlds that might truly resemble our own. The criteria for defining an Earth twin extend beyond simple orbital mechanics to encompass a complex combination of physical and environmental characteristics. The planet must possess a radius within about 20% of Earth's size, ensuring sufficient gravity to retain a substantial atmosphere while remaining small enough to maintain a solid, rocky surface. Its orbital period should place it within the conservative habitable zone of its host star, receiving stellar energy within a range that allows liquid water to exist stably on the surface without boiling away or freezing solid. The host star itself must meet specific criteria to qualify as truly sun-like. G-type stars, sharing our sun's spectral classification, provide the most direct analogs, burning hydrogen at rates that ensure stable energy output over the billions of years required for complex life to develop. These stars must also exhibit low levels of magnetic activity and stellar flares, which could strip away planetary atmospheres or sterilize surface environments with bursts of high-energy radiation. The star's metallicity, the abundance of elements heavier than hydrogen and helium, must be sufficient to support the formation of rocky planets with the chemical complexity necessary for habitability. Kepler 452b, discovered by the Kepler Space Telescope, represents one of the closest approximations to an Earth twin found to date. This planet orbits within the habitable zone of a G-type star very similar to our Sun, receiving only 10% more energy than Earth receives from our own star. Its orbital period of 385 days closely matches Earth's year, and the host star's age of about 6 billion years suggests a mature, stable system. However, Kepler 452b's radius is about 60% larger than Earth's, raising questions about whether it might be a super-Earth with a thick atmosphere rather than a true terrestrial world. The challenge of confirming Earth twins lies partly in the observational biases of current detection methods. Transit surveys like those conducted by Kepler and TESS are most sensitive to planets with short orbital periods, making it easier to detect hot, close-in worlds than planets orbiting at Earth-like distances from their stars. A true Earth twin, orbiting a Sun-like star with a 1-year period, requires at least 3 transit observations for confirmation, meaning a minimum 3-year survey duration, with additional time needed for follow-up observations and analysis. Radial velocity measurements face similar challenges when searching for Earth twins. The gravitational influence of Earth-mass planets on Sun-like stars creates velocity variations of only about 9 centimeters per second, requiring spectrograph precision that approaches the fundamental limits imposed by stellar surface turbulence and magnetic activity. Current instruments can achieve this precision only for the quietest, most stable stars, limiting the sample of stars that can be searched for true Earth analogs using this technique. The atmospheric characterization of potential Earth twins represents an even greater challenge, requiring next-generation space telescopes with unprecedented sensitivity and precision. A true Earth twin should exhibit spectroscopic signatures of water vapor, oxygen, and ozone in its atmosphere, potentially along with other gases that indicate active biological processes. The detection of these atmospheric components in the thin, tenuous signals from Earth-sized planets orbiting at habitable zone distances will require instruments far more advanced than those currently available. Statistical analyses based on Kepler discoveries suggest that potentially habitable Earth-sized planets may be relatively common, with estimates ranging from a few percent to 20% of Sun-like stars hosting such worlds within their habitable zones. If these estimates prove accurate, the nearest Earth twin might be located within 20 to 30 light-years of our solar system, close enough for detailed atmospheric characterization by future space telescopes, but far too distant for any form of direct exploration with current or foreseeable technology. The search for Earth's twin also involves understanding the role of planetary system architecture in maintaining long-term habitability. Jupiter's presence in our solar system appears to have played a crucial protective role, deflecting potentially dangerous comets and asteroids away from the inner planets, while also helping to deliver water-rich materials during the early stages of planetary formation. A true Earth twin might require a similar gas giant guardian, positioned at the right distance to provide protection without disrupting the orbital stability of the habitable world. The concept of an Earth twin extends beyond physical characteristics to include the evolutionary history that has shaped our planet's unique biosphere. Earth has experienced a complex interplay of geological, atmospheric, and biological processes over 4.5 billion years, including the gradual oxygenation of the atmosphere by photosynthetic organisms, the regulation of global temperature through the carbon cycle, and the maintenance of a protective magnetic field generated by our planet's active core. A true Earth twin would need to have undergone similar evolutionary processes, creating the intricate balance of conditions that makes complex life possible. Recent advances in theoretical modeling suggest that Earth-like planets might be more resilient than previously thought, capable of maintaining habitable conditions across a wider range of stellar and planetary parameters. The discovery of life in extreme environments on Earth, from deep ocean hydrothermal vents to highly acidic or alkaline lakes, has expanded our understanding of the conditions under which life might persist. This broader perspective suggests that while perfect Earth twins may be rare, worlds capable of supporting some form of life might be considerably more common throughout the galaxy. The psychological and philosophical implications of discovering a true Earth twin would be profound, representing confirmation that our planet's life-supporting conditions are not unique in the universe. Such a discovery would provide a cosmic mirror, allowing humanity to see Earth from a new perspective as one of potentially many worlds where the complex chemistry of life has taken hold and flourished. The knowledge that another blue marble exists somewhere among the stars would fundamentally alter our understanding of our place in the universe and our responsibility as stewards of our own planetary environment. Cosmic perspectives. Life's place in the infinite. As our understanding of exoplanets deepens and our catalog of distant worlds grows ever larger, humanity finds itself positioned at a unique moment in cosmic history. Possibly the first time a species on any world has developed the technology to detect and study planets orbiting other stars. This capability represents more than just a scientific achievement. It marks a fundamental transition in our relationship with the universe, transforming the ancient question of whether other worlds exist from philosophical speculation into empirical investigation. The sheer scale of planetary diversity revealed by exoplanet surveys challenges our preconceptions about what constitutes a normal or typical world. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, ice giant planets with diamond rain falling through their atmospheres, rocky worlds with surfaces hot enough to melt metal, and frozen planets where methane snow drifts across landscapes lit by the dim glow of red dwarf stars. Each discovery expands our conception of the possible conditions under which worlds can exist and evolve. Within this vast cosmic menagerie of exotic worlds, Earth emerges as both ordinary and extraordinary. Ordinary in the sense that rocky planets appear to be common throughout the galaxy, with many worlds falling within the size and composition ranges that characterize terrestrial planets. Extraordinary in that the specific combination of conditions that have allowed complex, multicellular life to flourish over billions of years may represent a rare convergence of favorable circumstances that occurs only occasionally in the cosmic dance of planetary formation and evolution. The detection of potentially habitable exoplanets provides a new context for understanding Earth's environmental systems and the delicate balances that maintain our planet's habitability. Climate change, atmospheric composition, ocean chemistry, and magnetic field dynamics, all the factors that influence Earth's ability to support life, can now be studied with the knowledge that similar processes are occurring on countless worlds throughout the galaxy. This cosmic perspective adds urgency to our efforts to understand and protect Earth's environment, as we recognize that habitable worlds may be precious and rare in the vast darkness of space. The search for biosignatures in the atmospheres of distant planets represents humanity's first serious attempt to answer the fundamental question of whether life exists elsewhere in the universe. The potential detection of atmospheric oxygen, ozone, or other gases associated with biological processes on a distant world would represent one of the most significant discoveries in human history, confirming that the chemical processes underlying life are not unique to Earth, but can emerge and persist under the right conditions on other worlds as well. Each potentially habitable world discovered adds to our understanding of the factors that influence planetary habitability and the likelihood that life might emerge and persist under various conditions. Worlds orbiting red dwarf stars, with their unique challenges of tidal locking and stellar flares, provide natural laboratories for studying how life might adapt to conditions quite different from those on Earth. Ocean worlds with subsurface seas, like Europa and Enceladus in our own solar system, suggest that habitable environments might exist in locations far from traditional habitable zones. The technological advances driven by exoplanet research continue to push the boundaries of what is possible in astronomical observation and data analysis. Instruments capable of detecting the tiny atmospheric signatures of distant worlds require precision engineering that approaches fundamental physical limits, driving innovations in optics, detector technology, and space-based observation techniques. These advances often find applications in other fields, contributing to progress in areas ranging from medical imaging to environmental monitoring. The growing catalog of exoplanet discoveries also provides crucial data for theoretical models of planetary formation and evolution. understanding how planets form from protoplanetary disks, how they migrate within their stellar systems, and how they evolve over cosmic timescales, helps scientists predict the likelihood of finding habitable worlds and assess the long-term stability of potentially life-supporting environments. These models, in turn, inform the design of future missions and help prioritize targets for detailed atmospheric characterization. As we peer deeper into space and discover ever more distant worlds, we are also looking backward in time, observing planets as they existed when the universe was younger and stellar systems were still forming. Some of the exoplanets we detect today formed billions of years before Earth existed, providing glimpses into the early epochs of planetary evolution and the conditions under which the first potentially habitable worlds might have emerged in the galaxy's youth. The philosophical implications of exoplanet science extend beyond the question of life's prevalence to touch on fundamental questions about the nature of habitability, the requirements for intelligence to emerge, and humanity's role in the cosmic story. Each discovery of a potentially habitable world expands the realm of possibility, suggesting that the universe may be rich with environments where the complex chemistry of life can unfold, each following its own unique evolutionary path across the eons. Now, close your eyes and imagine floating in the space between stars, surrounded by the gentle points of light that mark distant suns, each potentially accompanied by its own family of worlds. Some of these planets may be experiencing their first moments of habitability as atmospheric compositions stabilize and oceans begin to form. Others might host biospheres that have been evolving for billions of years, developing forms of life that we cannot yet imagine. In this vast cosmic ocean of possibilities, Earth continues its ancient journey, carrying within its atmosphere and across its surface the ongoing experiment of life that connects us to whatever other living worlds might exist among the countless stars scattered across the infinite darkness. The search for habitable exoplanets represents more than a scientific endeavor. It embodies humanity's deepest yearning to understand our place in the universe and our connection to the cosmos that gave birth to stars, planets, and ultimately, to us. As we drift off to sleep beneath our own star's gentle light, we can take comfort in knowing that somewhere among the billions of worlds that orbit the billions of stars in our galaxy, other planets may be experiencing the quiet miracle of habitability, their surfaces warmed by distant suns, their atmospheres cycling water and weather, their environments perhaps nurturing the delicate processes that transform lifeless chemistry into the vibrant complexity of living worlds. In the gentle darkness of space, separated by distances that dwarf human comprehension, these worlds continue their patient orbits, each carrying within its unique combination of size, composition, and stellar environment the potential for stories we have yet to discover. Some may be young worlds, still cooling from their fiery formation, while others may be ancient, having completed billions of orbits around stars that were already old when our sun was born. Together, they form a vast community of worlds, connected by the same physical laws that govern planetary formation and evolution, each representing a unique experiment in the cosmic laboratory, where matter organizes itself into the complex systems we call planets. As sleep approaches and consciousness gently fades, we can imagine these distant worlds continuing their eternal dance around their stars, some perhaps experiencing sunrise for the first time, as newly formed atmospheres clear to reveal the light of their host stars, others witnessing countless repetitions of day and night cycles that have persisted for geological ages. In this peaceful contemplation of cosmic possibility, We find ourselves connected to the vast network of worlds that populate our galaxy, each one a testament to the creative power of physics and chemistry operating across the immense scales of space and time that define our universe. The gentle rhythm of planetary motion continues across the galaxy, as worlds both familiar and unimaginably strange follow their orbital paths through space, carrying with them the endless potential for discovery, understanding, and perhaps even the recognition that in this vast cosmos of countless worlds, we are not alone.